All right, hello everyone, welcome to lecture 36. So today we will actually look at what properties turn out to be in terms of their microscopic statistical mechanical picture. So last class we left at a stage where we said okay, there is something called partition function. We defined partition function for a closed system. We said okay, so closed system is a system where the system and surroundings are not exchanging the particles, right. So there are n particles in the system, there are n1 particles in the surroundings, let us say. So the exchange of particles is not happening, but exchange of energies are happening, right. So based on that we defined our own microsystem, which is just one energy state, or in some sense the entire system is in that energy state, right. What is the probability that the entire system is in that one energy state versus the what is the probability, and then we calculated that as the number of states in the surrounding, mostly because in the system there is only one state, right. And we added, our system is now a combination of all these microsystems. So we added the total number of states by assuming that the system is in energy state EI or EJ or EK and so on and so forth. And we ended up with this this probability distribution function for a closed system, which is something of the form something like this. Pi is exponential minus EI by kBt by z, right, where z we said is actually what is called the partition function, and z has information about all the properties, right. So all the microscopic nature of the system, right. So z has information about the microscopic nature of the system. Z is the spy that thermodynamics had sent to spy on the systems, right. So to spy on the microscopic nature of the systems, that is what we said, and that conclusion we made because eventually towards the end of the class we showed that z is actually related to the partition function, the partition function z is related to the free energy, the thermodynamic free energy, the so called Helmholtz free energy, right. Okay, so far so good. Now we will see what is the use of so from thermodynamic free energy we know how to calculate properties, and we will calculate the properties by keeping in view what z is, right. And based on that we are now going to say what are these properties in terms of z and try to get a physical meaning for these properties, which is more than just saying that these equilibrium properties are some sort of restoring so they give you the magnitude of the restoring forces. Okay. All right. So that is what we will do. So let us again rewrite what z is. Z is just exponential of minus EI by kBt. Now if my problem is just this is the internal energy, right. So if my problem is just to do with so if I have let us say the internal energy of the system is determined by the polarization of the system, right. I am going to say EI, energy state, is actually given by, if my system has a polarization Pi, right. So Pi times the electric field in which it is sitting. Okay, so instead of EI maybe, okay, so electric field I am just going to write it as script E, okay, plus so this is the electrical energy plus xi times capital X, this is the mechanical energy, right. So internal energy, mechanical energy of the system, plus and so on and so forth. I mean, so if I have to add magnetic energy, I will add magnetic energy, right, and so on and so forth. So what does this mean? This means that my system, the electrical part of my system, has certain polarizations, right. So one part has this polarization, another part has this polarization, another part has this polarization, and so on and so forth, right. By the way, it is supposed to be displacement times electric field, but I am just going to look at the material perspective. A material gets polarized. Displacement is polarization plus some vacuum charges, right. That is what we have seen earlier, and that vacuum charges are nothing but epsilon naught E, right. But so so this is on the electrode of the capacitor, that is what we see the displacement, but Pi polarization is the is a material property, right. So, it is the dielectric, the property of the dielectric. So, I would rather use Pi, which is the polarization of or the dipole moment inside the material, rather than using di to represent the self energy of the system. Okay. So, the internal energy of the system. Okay. So, what this means is I have so many different configurations of polarizations in the system, and they all exist in some sort of an external electric field. They exist in some sort of a uniform electric field, right. So, then what is the energy of this configuration, what is the energy of this configuration, what is the energy of this configuration, and so on and so forth. So, so everything has an index. This is configuration 1, this is configuration 2, this is configuration 3. It is a so my system is a combination of all these things. So, it can have all these various polarization states in some sense, right. So, the system can have all these various polarization states, and so these polarizations, so every state of polarization has a certain energy, and that energy is given as Pi epsilon, right. Now, how you imagine these polarizations to be coexisting in the system or not coexisting in the system is up to you. Okay. So, there are certain microscopic polarizations in the system, and these polarizations exist in an electric field, and each of these polarizations, so classically defining, each of these polarization vectors defines a state of the system, right. So, here the state is defined not by the momentum of the wave function or something like that, it is just defined by the polarization vector, right. So, that is the state of the system, and the energy of this state is just given as internal energy of this state is just given as Pi epsilon, right. And similarly, so I have so many, so my system, the mechanical part of the system has so many states which are defined by different microstrains x1, x2, x3 and so on and so forth, right. So, there are different, you can imagine, so because ensemble average and time averages are the same, right. So, if you did not understand it, that is okay. So, you can imagine that so there are different parts of the system which have different microstrains, slightly different microstrains. So, the energy of that state of the system, right, or if I propagate the system through time, there are different microstrains that are generating in the system and changing as a function of time, right. So, a particular state has a has a microstrain of xi. I call it microstrain because a microscopic part of my system has this microstrain, right, and it is under a constant stress x, let us say it is under a stress x. So, the total energy, the mechanical energy of that state is given as xi times x. Okay. So, this is how I interpret this equation that I just wrote. Okay. So, now I have a partition function which is given as minus kbt ln z. Okay. And so z itself is equal to exponential of minus pi script t, that is the electric field, script t is the electric field, and minus xi capital X, right, by kt. Now, my system, right, so in different parts, right, so is defined by a polarization vector, right. So, this part has a polarization vector Pi, this part has a polarization vector Pj and so on and so forth, right. So, I am going to define, right now I am going to call Pi as some sort of an order parameter. I am going to define what this is later properly when I do Landau theory, yeah. So, I am going to define the order parameter quite robustly at a later part, but right now so Pi, so by knowing the Pi, I know what that system is, I know the state of the system, I know what sort of ordering is there in that system, etc. So, Pi is just called an order parameter for now. Let us just talk about Pi being an order parameter. So, this is in the electrical, it's a dielectric or electric order parameter. Xi is a mechanical order parameter. All the microstrains for different regions in my solid are mechanical order parameters, right. And this order parameter, can be exactly the same everywhere, or it can keep changing from region to region. That is why I have microstrains, right. But I divide my system into several microsystems, and the order parameter in these microsystems is different. Okay. So that is how I interpret the problem as per the materials, right. So the as per the material that I want to understand, material property that I want to understand. Okay. Okay. So this is sigma, right. So for over all i's. Okay. All right. So now we have so f for f is the same as phi 2, right. So we used phi 2, but here we are going to just say this is f in terms of statistical mechanics. And f is the Helmholtz free energy. We said so if I take df or d phi 2, that is minus s dt, right, minus E, so I am just going to talk in terms of minus p I sigma of that dE minus x I capital dx, right. So these are various different regions, right. So this is my total free energy of the system, right. So there are different polarizations in different regions, and the total energy is just given as this, right. So this is going to be my df essentially, right. From internal energy I can come down to df. Okay. So I mean we have actually looked at what df is, right. So earlier df is minus s dt minus p dv if I have p dv work, but if I do not have p dv work it will be d dE minus x dx, right. So different domains or different so microscopic regions will have different displacements or polarizations, and similarly microstrains, right. So different microscopic regions have different microstrains. Okay. So I am just going to write f as this expression. Okay. And so then I am going to define what is the okay. So thermodynamically let me just write it this way. So minus p dE minus x dx, right. So now I am going to define what is dou f by dou E and dou by dou E of that, keeping stress constant, keeping temperature constant, and that we have seen is nothing but some sort of so that will be dou p by dou E, right. Let's assume that tensorially all of them are in the same direction to be very simple, right. So that will be my susceptibility, right. So that is dou p by dou E, and that is nothing but susceptibility, right, or minus of susceptibility. Okay. So this is the electrical susceptibility, what I get as or dielectric susceptibility, right. So this we have seen earlier, we have seen dielectric susceptibility as a double derivative of a free energy, right. So that we have seen earlier. Okay. So now I have dou square f by dou E square is my susceptibility, right. Okay. But now I have a sniff into the microscopy of that. Now I want to understand really what susceptibility is, right. So then I am going to say f is nothing but minus kBT log z, right. So I need to invoke z instead of f, because z has information about all the microscopic features of the sample, right. Okay. So what is that? That is so dou f by dou E, right, dou by dou E, and that will be dou by dou E minus of that is susceptibility, right. So that will be minus kBT will just come out, right, dou by dou E dou ln z by dou E, okay, and so that will be kBT dou by dou E 1 by z dou z by dou E. Okay. So let us just write it in terms of z for the time being. So that is kBT. What I have here is there will be two terms, right. So one term is just dou square. So, I will get a 1 by z outside. So, I am doing a uv differentiation, right. So, I have a 1 by z that comes outside and I have dou square z by dou e square given constant stress etc. The rest of them are all constant, minus 1 by z square, but this time dou z by dou e, right, because the differential of 1 by z is minus 1 by z square dou z, right. So, dou z by dou z dou z by dou e whole square. Okay. So, you can keep, it is just differentiation by parts, right. So, you can clearly see that this is the case. Okay. Okay. So, we have quantities such as dou z by dou e. What is dou z by dou e, right? What is z? So, I want to understand what is dou z by dou e, right. So, what is z? Z is sigma exponential so what is it, pi e minus of that minus xi capital X, right. So, I am not really changing so I am just looking at the electrical part of the problem, not even the mechanical part of the problem. So, let me simplify z and then say that I am just considering the electrical energy. So, all my internal energy is just because of electrical energy. Mechanically I am not touching the sample at all, right. There can be microstrains etc., there can be some mechanical energy, but there is no mechanically it's an isolated system, but electrically I can exchange the electrical energy between the system and the surrounding, and there I will just simplify my z to be exponential of minus pi e actually by kBt, right. So, I have maybe I missed the kBt earlier, yeah, by kBt. Okay. So, kBt is there, right. Okay. So, pi e by kBt, right. Now, if I take what is dou z by dou e, keeping everything else constant, I have my stresses constant, I have my strains constant, I have my temperature constant, that would be a pi would come out exponential minus, this is not probability, this is the polarization, right. So, this is the polarization of a microdomain. I am going to write it as capital Pi, not small pi. Small pi I used it as probability. This is polarization. Sorry, let me write it properly. Small pi, capital small pi is polarization of a microdomain I. Right. Small pi is just the probability of the system existing in state capital Pi, that the system exists in state capital Pi. Now, what is small pi? Small pi is nothing but exponential of minus capital Pi e by kBt divided by z, right. So, this let us keep it in mind, right. Now, what is dou z by dou e? We need to look at terms like what dou z by dou e is. Dou z by dou e is sigma I, pi comes out, right, capital Pi comes out, not small pi, let us not get confused like me, times exponential minus capital Pi e by kBt. Actually, Pi by kBt will come out, right, 1 by kBt. Okay. So, and then there is a minus, is it? It is okay. So, we will see what that is. So, dou z by dou e is essentially minus 1 by kBt. So sigma of pi exponential minus pi e by kBt, right. Okay. Now, what is this quantity, right. So, if the probability of the system existing in state I is exponential of minus pi e by kBt by z, right. So, this is the probability of system existing in a state I, right. Then the probability so of the polarization of the system. If I look at the average polarization of the system, that is nothing but small pi, right, the probability that the system exists in a state I times capital Pi and average and sigma of that, right. So, this is how the average polarization is defined, correct. So, this is the polarization of the ith state times the probability that the system exists in ith state plus polarization of the jth state times the probability that the system exists in jth state plus probability that the system exists in some kth state times the polarization in the kth state plus so on and so forth. That is the definition of average polarization, right. So, if I am looking at this expression, right. So, yeah. So, okay. So, let me write, so what is 1 by z dou z by dou e, okay. So, this is just dou z by dou e, and 1 by z dou z by dou e is minus 1 by k b t, that comes out times sigma of exponential capital P I exponential minus P I E by k b t divided by, or so I am just going to write a bigger sigma here, I am just going to simplify this, divided by sigma over I again exponential minus P I E by k b t, okay. Now, what is this? That is equal to minus 1 by k b t sigma capital P I times, this is just small p I, right. So, this is z, this is the partition function, and this is exponential minus P I E by k b t. So, that is nothing but small p I, right. So, what I have here is 1 by z dou z by dou e, right, times k b t times this is nothing but your average polarization, okay. So, so it is sum of all the polarizations divided by the number of such states I have, polarization states I have. So, this is nothing but the average polarization, okay. So, be that as it may, or negative of that if the negative carries, be that as it may, okay. So, now what is 1 by z? There is another term here, right. So, if I go back, so I am actually looking at this person here, this equation, this is, I will write it as equation 1, right. So, in equation 1, what is 1 by z dou square, okay. So, let me write it in red. What is 1 by z dou square z by dou e square, right. Now, that so for dou square z, what comes out, right. So, from the probability, so again let us go back to z equal to exponential minus P I E by k b t, right, sigma of that. So, for dou square z by dou e square, what we get is P I square exponential of minus P I E by k b t, right. Again 1 by k b t comes out, sigma of that, right, and dou square z by dou e square, hence will 1 by z of that will be 1 by z of, this time the expression is so P I square sigma 1 by z of exponential minus P I E by k b t, and that is nothing but, this is nothing but the probability of the system existing in a state P I. So, that is P I square, which is the polarization square, times the probability that the system exists in a state P I, right. So, what is this? This is nothing but the average value of P I square, okay. the kBt also comes out, and so kBt times 1 by z dou square z by dou e square. Okay, so so this is the average value of pi square. Now, so this is the so signs I am not so I am not following the signs completely, but that is okay because this will work out. You can again go back and do the same exercise. Okay, so I have this term which is nothing but pi square, and I have this term which is related to pi, right, whole square, right. So, this is, so what I have is that my susceptibility, what I have defined is that the susceptibility is actually goes as pi square minus pi whole square. Okay. What is this quantity? This quantity is nothing but the variance or fluctuation of microscopic polarizations. Right? Every microscopic state has its own polarization, and these polarizations are fluctuating, right. So, or so if I have a system with so many number of polarizations that keep fluctuating over time, right. So it can be, so again I am assuming that the ensemble average is the same as the time average. So, over time if my states are changing, if these polarizations are fluctuating, right. So, then so if the fluctuations are large, then my susceptibility is large, right. So, susceptibility turns out to be some dou p by dou e. This is the macroscopic definition of susceptibility, right. But microscopically what I am saying is this is nothing but so I do not even need to apply an electric field to understand the susceptibility of the material. What I would rather see is, does this material has different polarization states it can exist in, right. If this material has competing polarization states it can exist in, or as I go in time, let us say these polarization states are fluctuating and evolving, right. So, I can take either one polarization state pi, and with time this polarization state become pj, pk, p, so it fluctuates a lot, right. So, there are, even here there are multiple polarization states, but that is happening in time, right, of a single microdomain. Or ensemble wise, right. So, spatially, right. So, there are multiple polarization states at a single time, right, spatially existing, right, and they are also temporally changing, right. So, with time they keep changing. So, there is accessibility to multiple polarization state. In general what these two statements mean is the system has accessibility to multiple polarization states, right, that it can fluctuate easily between one polarization to another polarization state, right. So, then this fluctuation is large, right. So, pi square minus pi whole square, this is the fluctuation, this is large, right. So, if this is large, then so my susceptibility is large. This gives me a design principle actually, right. I will so I will rather make materials where with so let us say I take a material with several domains, but these are not rigid domains, right. So, if they are rigid domains, this is just one state, correct. But these are several domains, and these several domains keep fluctuating, one domain changes into another domain and so on and so forth, right. So, domains fluctuate in time, domain polarization fluctuates in time, right, and there are several polarization states to which each domain polarization can go to, several polarization states. So, P1, P2, P3 etc., to which each of these domains can go to. Then my susceptibility is large, or this material can be easily polarizable, right. So, if the material can take several polarization states, right, even if I have if I prepare a material in this polarization state, but I have accessible states are accessible polarization states are 30, but initially the material is polarized in this fashion, let us say, okay. Then I apply an electric field, let us say in this direction, and I want the polarization to come and join the electric field. How easy is it for polarization to become from here to here, let us put it that way, okay. Now, if the material has access to multiple polarization state, it can start going from, okay, so one polarization state, second polarization state, third polarization state, and eventually the electric field will dictate that so the polarization follows the electric field. That is the average polarization. So, average polarization follows the electric field, much easily if the fluctuation in polarization is large, right. So, P square minus P square, right. This can also happen if average polarization does not need to be a single value, right. So, average polarization can be 0. Even if average polarization is 0, if there are so many states that are available, if the polarization is fluctuating quite high, I mean, so if the fluctuations in polarizations are quite high, that means the system can access several polarization states, then the susceptibility is large, right. So, one of the design principles to make materials that have large susceptibility is to throw in or is to make the system such that it can take several polarization states, right. So, I can make several domains that coexist with each other. So, what are called so there are what are called okay, so we'll come to examples later, but so that's the idea, right. So, if I put a system near its phase transition, right, so let us say there is a tetragonal system, right. So let us take the example of what is called PZT, lead, zirconium, titanium oxide, right, 1 minus XX, okay. So, PZT can exist in a tetragonal phase with polarization which is pointing up. This is the ferroelectric polarization, it is not the dipolar polarization, it is not the dielectric polarization, it is the ferroelectric polarization, spontaneous polarization which is pointing up. Average polarization is pointing up, right, in the tetragonal phase, right. But PZT, so if I play with X, can also have what is called a rhombohedral phase, right, where the average polarization points in this direction, right. Now, the tetragonal phase has so how many it can point up or down or this way or this way or this way or this way, depending on which domain of tetragon is the PZT grown in. So, it can have 8 different configurations. The rhombohedral phase can have so how many 6 different configurations. The rhombohedral phase has 4 body diagonals. So, I mean the polarization is in the 1 1 1 direction of a cube, right. So, that becomes the rhombohedral phase. So, you have 8 different configurations. Sorry. Okay. So, if I make a material which is at the phase boundary of the rhombohedral phase and the tetragonal phase, this material can exist in 14 different configurations, right, which can microscopically change, right. So, region to region the polarization is changing, or so the fluctuations so they can exist over time or over space, right. So, both of them are okay, right. and that becomes a very soft material. So, then so because of so many different polarization configurations that the system can take, so this becomes a soft material, in the sense that since so many polarizations states are stable polarizations, right. So, even when I apply an electric field, I can easily move to these polarizations, so which are stable in configuration, and so I can easily switch from I can easily follow the electric field, right. So, that's the idea. So, it's a very soft material, it can get easily polarized, right. So, but the polarization, the easiness of polarization depends upon the fluctuations in polarization, right. So, polarization as an order parameter. Okay. So, if there are fluctuations in polarization as an order parameter, then the system becomes easily polarizable. Now, that I can take a system where average polarization is 0. So, this is just a paraelectric, or this is just a what is called a dielectric system, not ferroelectric. I do not need a ferroelectric material. I can take a dielectric material where average polarization is 0, right. But so if I polarize the material, I can apply electric field and still change the value of average polarization, right. Now, I can polarize the material in a certain direction, and if I polarize it in this direction, that is a stable polarization configuration, right. So, that configuration exists, it is one of my microstates, right. I can so this is another energetic polarization state that also exists, right. This also exists, albeit with different energies, right. So, if all these polarization states exist, if I have some many such polarization states, then so when I apply, the way to understand this is when I apply an electric field, then so average polarization should follow the electric field, right. So, should follow the electric field. So, all these microscopic polarizations that are there, they try to align with respect to the electric field quite easily, because if this state exists, this state also exists. So, it will jump from this state to this state, this state to this state, and eventually becomes this, right. So, this domain or this domain, for example, will jump from this to some other state, this to some other state, and all these states do exist, right. So, it will suddenly follow the electric field, right. So, it will be easy if I have so many configurations in which I can exist, it will be easy for me to travel from so to do whatever you want me to do, right. So, if I have access to so much of money, right, and then so if you say, okay, I have to do this, I will easily spend money and do it, right. So, I'm a soft target, right. So, that can do a lot of things, right. So, that's the rough analogy in some sense, right. So, if I have access to so many configurations, I can go from configuration to configuration and eventually follow the electric field, and that is an easy thing to do, right. So, that is why my susceptibility is large, because susceptibility tells me how easily am I polarizable, or as is the material polarizable. Okay. So, let me show you actually that this is the phase diagram I am showing here is I have lead zirconate on this side, I have lead titanate on this side. Okay. The idea, okay, so this is a rhombohedral phase, lead zirconate is in a rhombohedral phase, this is some low temperature rhombohedral, high temperature rhombohedral. Lead titanate is in a tetragonal phase, right. So, this is rhombohedral, this is tetragonal, but at about 48% of zirconium of titanium composition, right. So, 48%, not 50%. I have this boundary, right. So, this boundary, so at this boundary I can say that, right. So, if I am at this boundary, if I am at 48% titanium composition, I am at this boundary, right. At this boundary, a little bit of compositional fluctuation will put me in rhombohedral phase this way, right. A little bit of compositional fluctuation that way will put me in tetragonal phase, right. So, so if I apply an electric field, I can simply, and this also translates to fluctuations in polarization. If I apply an electric field, and I want to polarize this along, the direction of electric field, which is, neither tetragonal direction nor rhombohedral direction, then so the tetragonal phases, the tetragonal side, if it fluctuates to the tetragonal side, it can either fluctuate to one of the 6 configurations, right. So, these are all the stable configurations in the tetragonal side. If it fluctuates to the rhombohedral side, it can fluctuate to one of the 8 different configurations, right. So, altogether I have 14 different configurations through which the system can move through and move to the final configuration that the electric field is determining, right. As a result, PZT, this is called PZT, lead zirconium, lead titanium, right. So, gotten by alloying lead zirconium oxide and lead titanium oxide, one in each other. PZT will have a huge polarization, huge susceptibility near this phase boundary, right. So, near what is called so this is what is called a morphotropic phase boundary. Okay. So, so this is one such, so here it is going to phase transition from by changing the composition, PZT is going to phase transition from a rhombohedral phase to a tetragonal phase, right. So, if I am right at that boundary, almost at that boundary, I will always have microscopic fluctuations, right. So, let us take the case of PZT, lead zirconium 52%, titanium 48% and O3. So, this is the phase boundary, right. Now, at the phase boundary, so a little bit of fluctuation to this side, if it is zirconium 0.52 minus delta, that becomes a rhombohedral phase. If it is zirconium 0.52 plus delta, that becomes a tetragonal phase, right. And here I have 8 configurations, here I have 6 configurations. So, the number of polarization configurations that my system can access is huge, right. I have 14 configurations. So, if I have to force my system to go into a certain average polarization, it is easy to do because it can jump from one configuration to another configuration and easily go there. And that makes my so the fluctuations are large, right. So, even with time so this can just fluctuate between this polarization, that polarization and so on and so forth. And so, that translates to my property, which is susceptibility, that is nothing but a manifestation of these fluctuations, right. So, manifestation of these fluctuations, I give it one name, I call it susceptibility, and this susceptibility is large. So, I can measure susceptibility. So, I can actually measure the manifestations of these fluctuations. Right. By measuring, I just do a macroscopic measurement of susceptibility, and that means if susceptibility is large, my system has these immense configurations of polarization that are fluctuating very dynamically, right. So, this is large. Okay. So, that is yeah, and the fluctuations are largest near some sort of phase boundaries, right. So, we have seen that in PZT there is what is called a morphotropic phase boundary, okay. And in this morphotropic phase boundary, the fluctuations are the largest. Okay. So, fluctuations are large in near phase boundaries, right. So, okay. There are these so PZT is one such material, but there are these materials where so I can have not 14 configurations so I can have one domain or one nanoscopic region, right. So, or microscopic region in one polarization direction, another microscopic region in another polarization direction and so on and so forth. The so called what are called polar nano regions, but these polar nano regions, if I increase the temperature, right. So, they are also not static in some sense, but they also keep fluctuating, right. Okay. So, if I have so many configurations of polarizations, right. So, in my material I have a set of bunch of polar nano regions, even then so my susceptibility is large, right. So, here so I can consider this material as some sort of a ferroelectric glassy material, right. So, because I have so much of disorder in polarizations, they all exist in these nanoscopic regions, but they are fluctuating, there is so much of disorder, right. So, it looks like a glass, it is not so it is not that every part has the same polarization, right. So, it is not a crystalline like polarization arrangement, whereas it is so one part has some order, some medium range order, second part has some other medium range order, third part has some other medium range order, and so on and so forth. This is the model for a glass, right. So, or what is called as ferroic glass, ferroelectric glass, right, or these materials are also called relaxor materials, right. So, in relaxor materials you have also these high susceptibilities, because you have so many polarization configurations, right. Okay. So, susceptibility is large. One of the examples of relaxor materials is, okay, so I have lead, so I have manganese, I have magnesium, I have niobium, right. In the same B site, this is the A site, these are all perovskite materials, this is the B site, 1 minus X, this is X, I have O3, okay, and I can still alloy it with lead titanate, right. So, lead titanate itself will have its own polarization, so directions, 6 different polarization directions. Here when I alloy it with manganese and niobium, so it just becomes too many different polarization directions, right, that I cannot, so that it becomes a glassy like polarization order, and this glass like polarization order yields lot of susceptibility, right. So, so this is what is called PMNPT. This is also a very good material if you want to have high dielectric constants, okay. Yeah. So, then so you can think of generating these materials with high dielectric constants. There are materials that are available with high dielectric constants, something like strontium titanate. The net polarization is 0, but the polarizations fluctuations, right. So, strontium titanate so can exist in different polarization states, right. So, the net polarization is 0. At a unit cell level, cubic phase is what is preferred, but it is easy to sort of induce these microscopic polarizations, so that the average polarization is still 0, right. So, in strontium titanate here also I have a lot of fluctuations in polarization, right. So, giving rise to a susceptibility of about 300 or whatever that value is, or 200 to 300, right. So, this is a high susceptibility material or high dielectric constant material, whereas if I take something like hafnium oxide, this is a harder material, right, where dielectric constant or susceptibility is only 19 or 20, right. So, so although I have these polarizations, I can create these microscopic polarizations, but they do not fluctuate, right. So, it is harder for any sort of configuration to change from so to follow the electric field, right. So, this is much harder material, right, much harder. If I go to silicon oxide, the dielectric constant is much smaller, right. So, it is I forget the value. So, here the dielectric constant is 19, it goes from 19 to 30 depending on whether this is a crystal or not, whereas for silicon oxide the dielectric constant is much smaller than hafnium oxide. So, this is even more harder dielectrically. So, you cannot polarize silicon oxide, because intrinsically there are no fluctuations in polarization in silicon oxide, right. So, everything is sort of centrosymmetric position, I am not able to create. So, I have silicon, oxygen, let us say oxygen here, right. So, if I have to create any sort of polarization, I have to move silicon away from its centrosymmetric position, right, or I have to move oxygen, right. So, oxygen also has a tetrahedron. I have to move oxygen away from its center of tetrahedral position. Now, moving oxygen anywhere in the vicinity is a very high energetic process. So, oxygen just does not want to move, right. Oxygen is stable there, right. So, I cannot really create these micro states of polarization so easily. I have to apply large enough field so that oxygen crosses that activation barrier to go from, let us say, here to here or something. It has to distort to a certain place atomically, right. So, that I create that polarization, and there are not many such places where it can go to with a reasonable activation barrier. As a result, the dielectric constant will be less, right. So, you cannot easily polarize this material, the number of configurations are less, okay. So, that is the way to understand this fluctuations, right. So, and fluctuations, how they relate to a high dielectric constant, okay. So, so tomorrow in the next class we will look at so fluctuations in microstrains. that will give me a softer mechanical material or a mechanical material with a less Young's modulus, right. So, what are called all these high entropy alloys, they tend to be softer compared to metals, right. So, we will look at that example, and then we will look at what are these electromechanical properties really. So, typical electric properties are just fluctuations of order parameters, typical mechanical properties will also be fluctuation of mechanical order parameter, but what are the typical electromechanical properties, right. So, the electric part needs to talk to the mechanical part there. So, the correlations come in. Okay. So, we'll check that out in the next class. Okay. So, with that let us conclude this class.